Everyone, what we want to do in this section is talk about this idea of ramps and how ramps allow us to do work. So you've got two options. You can lift the heavy object straight up from the ground, straight up into that truck, or you can push it along the ramp. Which one allows you to do more work? To show you an example of this, let's do this right now. So for our setup here, the heavy box is going to be this mass, and I've got a spring scale. The spring scale tells me that to hold this object at rest, it's right around 10 newtons, 9.8 exactly. So what I'm going to do is I'm going to lift this up from the table to the top of the ramp. Watch the force sensor. So there you go. The force was 10 newtons from the level ground to the top of the ramp. If I measure that out, it's about 27 centimeters. So it took 2.7 joules of energy for me to lift that from the ground to here. Now let's look at me pulling it along the track. Watch the force sensor as I pull up the ramp at a nice steady speed. Force was a lot less. Force was hovering around 3 newtons for the entire pull. And then now I went about 90 centimeters. So let's see how much energy we used in both scenarios. So here's our scenario. The scenario was me lifting that box straight up the ramp. It took about 10 newtons of force, and I went up 0.27 meters. So multiplying the force times the displacement, because we're asking which scenario had more work done, I got 2.7 joules. I got 2.7 joules of energy. Now let's look at the scenario of me dragging it up the ramp. If you noticed, the force was a lot less. I only had to push with 3 newtons of force. It was a lot easier to lift that weight. Trade-off was I went 90 centimeters compared to the 27 centimeters of just deadlifting it straight up. And if you take 3 newtons times 0.9 meters, I get 2.7 joules. So in both scenarios, I actually did the same amount of work. I actually did the same amount of work whether I was lifting straight up in the air or taking the block and dragging it along the ramp. The trade-off was I had to travel a lot bigger distance, but I was allowed to use less force. And that's the advantage of using machines like ramps and pulleys and levers and all those things. You don't have to lift the full weight, but you're going to have to travel a much bigger distance. You're going to get the same amount of work out whether you do it lifting straight up or up the ramp. So there can be work done that's along a curved path. And we have work done along curved paths. Using dot products or integrating might be the best way to solve your scenario. So the question here, you've got a curved slope. The question is, what is the final velocity of the skier when they reach the bottom of the slope? If we set this up, let's draw a free body diagram and look at the work done to figure out our final velocity. If work is done, our kinetic energy will change. Okay, so what we have here is the skier going down the hill, and they're going to be going in this displacement. That vector R displacement has 2 pieces that make it up. It has an X displacement and a Y displacement. So what we want to look at are the forces. Since we know work is the integral of force dotted with displacement, if work is done, the person will change their kinetic energy. And since the skier is going down the hill, most likely they are going to increase their kinetic energy. So we got to look at the net work here. If we look at the work done by the normal force dotted with the displacement is the normal force pointing up off the plane, the displacement being down the hill. If you look at that, there is no work done because they're perpendicular. If you need more proof of that, take the force dotted with the displacement and multiply by the cosine of the angle between them. And the cosine of the angle between those two is 90 degrees. So again, normal force has no work done. So we got to look at gravity then. The work done by gravity is the force of gravity dotted with the displacement. So if we look at the force of gravity is straight down. So that's mg in the negative j direction. Dotted with the displacement is in the x direction, which is I, and the y direction, that is j. So if we know anything about dot products, when we do a dot product here, we're going to have to multiply the j dot j. J dot I gives us nothing. So the work done by gravity ends up being mass times gravity times the change in y. Call that change in y negative, so again, we can just look at the work done by gravity as being mass gravity times the y displacement. Since we see that there is work done by gravity, we know that work causes a change in our kinetic energy. The work done by gravity here is mg delta y, and our kinetic energy went from no kinetic energy in the beginning to having kinetic energy at the end. And we get 1/2 mv squared. The masses do cancel out, and if you want to solve for velocity, it's going to be 2 times the gravitational acceleration times y. Square root gives us our final velocity when we reach the bottom of the hill. So regardless of our mass, any object going from the same height down to the ground should reach the same exact velocity, friction-free. So we got to talk about the work done by friction then. What kind of work does friction do on an object? Here's our box again. Our box has the force of gravity acting down, has the normal force acting up at an angle, and has a frictional force pulling back. So there are 3 forces acting on our box: friction, normal, and gravity. And let's say that we're being displaced down the hill. The box is sliding down the hill. If that's the case, we want to look at the work done in all scenarios. We said the normal force is going to do no work. It's perpendicular to the displacement. Gravity is going to do some of the work. The x component of gravity is pointing down the hill. So gravity is doing some positive work, but I can see frictions against the motion. Friction is going to try and resist this and do negative work as we slide down the hill. So if you just want to focus on the work done by friction, which is something you might have to encounter, the work done by friction, the equation is no different. It's the force of friction multiplied by the displacement. The force of friction, though, remember, is mu multiplied by our normal force. And our normal force in this case ends up being the cosine component of gravity. So it's going to be mg cosine of theta multiplied by the displacement. And you might as well throw that minus sign in there because friction is going to do negative work. Well, what if the box was sliding up the hill? Force of friction would resist that. The box is sliding up the hill with a positive displacement, and friction is going to resist that and try to slow you down. And if you look at this, friction is backwards, displacement is up the hill, friction is still doing negative work. Friction is trying to take energy out of your system. Friction, even though it's fun, always tries to ruin the party. So that's how you can calculate the force of friction. This works for a box sliding on a hill, but if you have a box on a level surface, your normal force will be different. But make sure you use your kinetic coefficient of friction multiplied by your normal force multiplied by displacement, and you'll be able to calculate the work done by friction every single time.